Imagine this specific scenario. You are an AI engineer. You've spent, I don't know, weeks building this incredibly sophisticated system to predict house prices in Mumbai.
Right, a classic project.
Yeah. So you type in the details for a test case, right? You put in 2,000 square feet. It's sea-facing, 3 bedrooms.
Yeah.
Your model processes all that data and confidently just spits out a number. It says 80 lakh rupees. But the real market price...
That would be way off.
Oh, completely. The real price is 1 crore.
Ouch.
Yeah, that is a massive gap. That's a 20 lakh rupee mistake. And the question for you as an engineer isn't just, why was it wrong? The real question is, how does the system automatically detect that massive error and fix it without you having to go in and manually tinker with the Python code?
That is exactly what we call the prediction gap. And honestly, it's the very first nightmare every AI engineer faces.
Because if you have to fix it manually...
Right. If you're writing statements to fix it, it's not AI. It's just a giant glorified spreadsheet.
Exactly. It completely defeats the purpose. Or let's take scenario number 2. You're training a model, right? And you're staring at the error rate on your dashboard.
Like watching paint dry sometimes.
Seriously. But you want it to go down, obviously. You want the model to get smarter. But instead, the error rate is just jumping all over the place.
It's spiking.
Yeah, spiking, flatlining, refusing to stabilize. We call this the convergence trap. How do you even know if your step size is too fast or if your model is just fundamentally broken?
And that's the exact moment most beginners just completely panic.
They assume everything is ruined.
Yeah, they think their code is buggy or the data set is absolute garbage, when really it's often just a single number that's off.
Just one hyperparameter. And then there's the third nightmare. I think this is the sneakiest one. The memorization failure.
Oh, that one hurts because it feels like a win at first.
Exactly. Your model takes the practice test, your training data, and it gets 100%. A flawless score.
You think you've built an absolute genius.
Right. You're ready to deploy. Then you release it into the real world, into production, and it just fails miserably.
Because it didn't actually learn a single thing.
Nothing at all. It just memorized the answer key.
It's exactly the difference between truly understanding a subject and just memorizing a textbook before an exam.
Right.
I mean, one works in the classroom, but the other completely fails in real life.
Yeah.
And in industry, that failure costs real money.
So these are the 3 dragons we really have to slay today in our deep dive. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
It is so great to be here. And today is really pivotal for anyone listening because we are finally moving away from the magic of AI.
Yeah, we're totally done with the hype.
We're peeling back the curtain. Our mission for this deep dive is to help you develop a very specific mental model, which we like to call the learning engine.
The learning engine. I love that.
Because a lot of people, especially those coming from basic Python backgrounds, they think AI learning is this mystical, almost biological process where the computer literally thinks.
Like it has a brain in there.
Right. But it's not. It is just a highly mechanical loop.
A loop?
Yes. Prediction, error, adjustment, repeat. That's it.
Prediction, error, adjustment, repeat.
Exactly.
Yeah.
And today isn't about, writing complex differential calculus on a whiteboard.
Thank goodness.
Right. We will touch on the concepts, but it's really about understanding that mechanical loop. We want to move you from thinking of AI as this magical black box to understanding exactly how a machine mechanically reduces its own mistakes.
That makes perfect sense. So let's really set the stage here. We need a running case study to anchor all this abstract theory. Let's stick with the house price prediction scenario from the intro. Okay.
Perfect. It's the classic hello world of machine learning for a very good reason.
It's super intuitive.
It is. We have a clear goal, predict the price of a house. And to do that, we have information, or what we call features.
Like the area of the house in square feet.
Exactly. Area and, let's say, the number of rooms.
Okay, so I have my inputs. 1,000 square feet, 2 rooms. And I want an output, the price.
Right.
But as someone who knows traditional Python programming, how does the computer actually structure that? Normally, I'd just write an if statement, like if square feet 1,000 price equals 50 lakhs. Why don't we just do that?
Well, because the real world is incredibly messy. You can't capture it with if statements.
It's really variable.
Exactly. What if it's 999 square feet?
Right.
What if it's 1,000 square feet, but it's in a terrible neighborhood or it has no windows? You would literally need 1 billion if statements to cover every combination.
Which is impossible to write.
Impossible. So instead, we use a model. And I want you to think of the model not as a list of rules, but as a structure or a formula.
Like a math equation.
Yes. In its absolute simplest form, it looks something like this. Price equals the area multiplied by, let's call it weight day, plus the number of rooms multiplied by weight 2, plus a bias.
Okay, let's unpack that a bit. You said weights. These are the parameters of the model.
Yes, exactly. Imagine the model is a student sitting in a classroom. The weights are essentially the knobs inside the student's brain that determine how important something is.
Importance. So how much something matters to the final answer?
Exactly. Does the area matter more than the number of rooms when determining the price?
Well, I would assume area matters way more. A tiny house with 10 really cramped rooms is still a cheap house.
Right, so intuitively as a human, you know that area drives the price more than the room count.
Yeah.
The model represents that human intuition with numbers. If area is super important, weight 1 will be a big number.
Okay.
And if the number of rooms doesn't really matter as much, weight 2 might be a tiny number. The model turns these knobs, these weights, to adjust how much influence each feature has.
So a weight is quite literally how much weight or importance we give to that specific piece of data.
Just buy on.
That makes a lot of sense. But you also mentioned a bias. What is that? Like a personal preference the model has?
In a weird way, yes. Think of bias as the starting baseline.
The baseline.
Yeah. If a house had 0 square feet and 0 rooms, which is obviously impossible, but just bear with the math here, what would the base value be?
Right. Mathematically, what's the starting point?
Exactly. Maybe there's a base cost just for the land itself or the registration fees.
Oh, I get it. It's like a cover charge at a club. You pay it just to walk in the door before you even buy any drinks or do anything.
That is a perfect analogy. The bias is the intercept. It is where you start before you even look at the specific features of the house.
Got it. So parameters, which are the weights and the bias together, are the things the model uses to make its guess.
Correct.
Now, here is where my Python brain gets stuck. In traditional coding, I declare my variables, right? I type x equals 10. Who declares these weights in a machine learning model? Do I set them?
This is the critical shift in your mental model. We, the human engineers, do not set these weights manually.
Really?
If I went in and typed weight 1 equals 5,000, I would be the one learning and doing the work, not the machine.
So where do they come from when you first hit run?
Usually. Pure randomness.
Wait, random numbers?
Yes. When we start training, we initialize these weights randomly. We essentially lobotomize the student before the first class.
That sounds rough.
Well, the model starts out completely stupid. It might actually guess that area is worth negative money.
So it might start by predicting that a bigger house is somehow cheaper.
Potentially, yes. Because it starts with random garbage numbers. The whole process of learning is simply the act of the model adjusting those random numbers step by tiny step until they stop being garbage and start reflecting reality.
That is a wildly different way of thinking about writing software. Normally, we want our code to be absolutely perfect from line 1. But here, we are intentionally starting with broken code and asking it to fix itself.
Precisely. We are building a self-correcting machine.
Okay, so the model is the student. The weights are its current and probably very wrong knowledge. Now, the student takes a test. It predicts a price. It says, I think this house is 80 lakhs. But the real price is 1 crore. The student is wrong.
Very wrong. And this brings us to the second crucial part of our loop, the feedback loop. In technical AI terms, we call this the loss function.
The loss function. That sounds very serious and mathematical.
It is mathematical, but I want you to think of it not as a formula, but as a disappointment meter.
A disappointment meter. Okay, I really like that.
Because that's what it is. It measures the exact distance between the model's guess and reality.
Yeah.
So in your example, the prediction is 80, the actual is 100.
So the loss is the gap. It's that 20 lakh difference.
Exactly. But is the goal just to get that specific number to 0?
Ideally, yeah, right. 0 disappointment.
Yes, but the loss function gives us something much more valuable than just a final score. It gives us direction.
Direction, like a
Sure.
compass.
Exactly like a compass. If the loss is huge, the compass is screaming, whoa, you are way off, turn around. If the loss is small, it whispers, you're getting warmer. Keep going just a little bit more in this direction.
Wait, I want to dig into the math just a tiny bit here. You said we calculate the gap. Is it literally just subtraction? 100 minus 80?
Often, no. We usually do something called mean squared error.
Okay, so we square it.
Yes. We take that 20 and we square it to get 400.
But why square it? Why make the number artificially bigger?
To severely punish the model.
Wow, okay. That sounds harsh.
It is necessary discipline for the machine. Think about it. If the model is off by 2, squaring it gives 4. But if it's off by 10, squaring it gives 100.
Oh, I see.
Squaring ensures that massive mistakes are punished exponentially more than tiny mistakes.
Yeah.
We are essentially screaming at the model. Do not be vaguely wrong on the big things. Be precise.
So the loss function isn't just a scoreboard at the end of a game. It's a real-time critique. It tells the model exactly how badly it messed up.
Exactly. And this disappointment meter creates a landscape. We really need to visualize this to understand the engine.
Okay, paint a picture for me.
Imagine a massive graph where the vertical axis represents loss or disappointment. We want to be at the very bottom, at 0. 0 disappointment.
Which means the prediction is absolutely perfect.
Right. High loss means you're high up on a peak. Something is fundamentally wrong. Low loss means you're down in a valley, refining your knowledge. The loss function is the only guide the model has.
Because without it, it's just guessing blindly.
Exactly. It doesn't know if 80 lakhs is a brilliant guess or a terrible one until the loss function calculates that gap and places it on the landscape.
Okay, I have the model, the student, and I have the loss function, the disappointment meter. The model makes a guess. The meter screams, "You are 400 points off."
Yes.
Now what? How does the model actually fix it? Because this is the part that always feels like pure magic to me.
And this is exactly where the magic evaporates and becomes pure, elegant mechanics.
This is the adjustment phase of our loop. And the specific method we use is called gradient descent.
Gradient descent. That is a term I hear thrown around constantly. It
Okay.
always sounds like the title of a bad action movie to me, like Gradient Descent, The Fall.
It really does.
Mm.
But the analogy is actually very physical and grounded. I want you to imagine you are standing on top of a massive mountain range,
Okay.
but it's pitch black outside. You can't see the horizon, you can't see the sky, and you definitely can't see the village at the bottom of the valley.
So I'm stranded on a mountain, basically blindfolded.
Right. And your only goal is to get to the lowest possible valley, the absolute bottom point. In this analogy, the height of the mountain represents your loss, the error.
So being high up on the peak means I have high error, which is bad. And being deep in the valley means low error, which is good.
Exactly. You want to get to the bottom, but you can't see a thing. So what do you logically do?
I guess I would feel the ground with my feet. I'd feel which way the slope is pointing. Exactly. You feel the slope. That's slope. That is the gradient. And the step you take downwards, that is the descent.
Gradient descent. I want to push on this feeling the slope idea, though, because it sounds a bit too human. The Python model doesn't have feet.
True.
When we say it feels the gradient, we're actually talking about calculus, right? We're talking about derivatives.
We absolutely are.
Yeah.
And I'm really glad you brought that up because feeling is just a metaphor for a very precise mathematical operation.
Right.
What the model is actually doing underneath the hood is taking the partial derivative of the loss function with respect to every single weight.
Okay, let's de-jargon that for our Python devs. Partial derivative with respect to the weight.
Yeah.
If I'm looking at my price as area weight formula, what is the derivative actually telling the computer?
Think of the derivative as sensitivity.
Sensitivity.
Yes. It is asking the math. How sensitive is my overall error to a tiny, tiny change in this specific weight?
Oh.
If I tweak the weight for area by just 0.001, does the total error scream in pain and jump up? Or does it drop? Or does it barely notice?
So if the slope in the mountain is really steep, the error is super sensitive. A small change in the weight causes a massive drop in the error.
Exactly. And what if the slope is totally flat?
Then the error doesn't care. Changing that specific weight isn't going to help me get down the mountain.
You've just perfectly defined the gradient part of gradient descent. It's a collection or a vector of sensitivities.
Okay.
And this brings us to the descent part. The model looks at all these sensitivities and says, okay, the error is screaming the loudest about the area weight. Let's fix that one first.
It prioritizes the biggest fires.
Sort of. It actually moves every single weight simultaneously,
Yeah.
but proportional to how much that specific weight is contributing to the error.
Wow.
This is why the mountain analogy is sometimes a little dangerous, because it implies you're walking in standard 3D space.
Like hiking.
Right. But in reality, an AI model might have 1,000,000 parameters. So you're blindly walking down a mountain in a 1,000,000-dimensional hyperspace.
Which is completely impossible to visualize without hallucinating.
It truly is. But the math holds up perfectly, whether it's 2 dimensions or 2,000,000. You just follow the slope down dimension by dimension.
So the model asks a very specific question for each parameter. If I slightly nudge weight 1 up, does the error go up or down?
Yes. It's checking the slope of the error for that exact variable. If increasing the weight makes the error go up, the model says, oops, wrong way, and it decreases the weight instead.
It's just a mechanical check. Nudge, check error, take a step down.
Correct. It always moves in the exact direction that reduces the loss. And it does this for every single weight, all at the exact same time.
That is incredible. And that actually brings us to a crucial concept that solves one of those specific nightmares we talked about in the intro.
Ah, the size of the step you take.
Right, the convergence trap, the error rate jumping all over the place.
Exactly. We call the step size the learning rate.
The learning rate.
Yes. You're on that mountain, you've used your derivatives to figure out exactly which way is down, but now you have to make a decision. How hard do you jump?
And this is a hyperparameter, right? The model doesn't inherently know how fast to learn. We have to explicitly tell it.
Correct. And let me tell you, it is arguably the most frustrating hyperparameter to tune in all of engineering.
Why is it so hard? Is it just a Goldilocks situation, like too hot, too cold?
It is, but the consequences of getting it wrong are often invisible, and they are very expensive.
What do you mean expensive?
Let's say your learning rate is too low. Say you set it to 0.000001. You aren't just learning slowly. You might run your training cluster for a solid week, burn $5,000 in AWS GPU credits.
Oh, wow.
And your error rate will have moved from 50% to 49.9%.
Ouch. So you're literally burning cash for zero actual learning. It's like trying to walk down Mount Everest by moving 1 millimeter every single day.
Exactly. You'll die of old age before you reach the valley. But the alternative is actually much worse.
Setting it too high.
Yes. If you set it too high, you get what we call the exploding gradient.
That sounds like a Michael Bay movie. Exploding gradient. What actually happens in the math?
You calculate the slope, you point downhill, but you take a step so massive that you don't just miss the bottom of the valley. You overshoot it completely and land on a high peak on the exact opposite side of the mountain.
Oh, man. So you're worse off than when you started.
Much worse, because now the error is higher. So the gradient screams, whoa, huge error, go back down.
But because your step size is still set too high,
you jump massively back across the valley, missing it again, and landing even higher up the original slope.
It's a pendulum.
Exactly. You start bouncing back and forth across the canyon, gaining energy and air every time, spiraling completely out of control until the computer literally returns nan, not a number. The model entirely breaks.
So you're not just failing to learn, you're actively destroying the model.
Precisely. This is why modern engineers don't just pick one static number. We use what we call learning rate schedulers.
Schedulers.
Yeah, we start with a big step size to get close to the general area of the valley quickly. Then, as we get closer, we decay the rate, we make the steps smaller and smaller, to carefully tiptoe right into the bullseye without overshooting.
Oh, that makes total sense. It's like parking a car. You drive fast on the highway to get to the parking lot, but you crawl at 2 miles an hour when you're actually pulling into the spot.
That is the perfect mental model for a learning rate scheduler.
That completely explains why the error rate refuses to stabilize sometimes. It's the step size.
Okay, so we're stepping down the mountain.
Yeah.
But I have a logistics question.
Sure.
Do we calculate the error and take a step for every single house in our data set one by one?
Yeah.
Or do we look at all the houses at once and then take a step?
This is a classic logistics problem in ML, and it introduces two very important terms, epochs and batches.
Define them for me, because people mix these up all the time. Let's start with an epoch. An epoch is one full pass through your entire training data set.
Okay.
Going back to our student analogy, it's like reading the whole textbook from start to finish exactly once.
Got it. So if I have 10,000 house records in my database, one epoch means looking at all 10,000 houses.
Yes, but computers have physical limits.
Right, RAM.
Exactly. Memory limits, computational limits. We usually can't just shove all 10,000 houses into the GPU's brain at the exact same millisecond to calculate one giant error gradient.
It's like trying to memorize the entire textbook in one single glance. Your brain would just blue screen.
Exactly. So we break the data down into batches, small, manageable chunks.
Okay.
Maybe we look at 32 houses, calculate the error for just those 32, and take a small step down the mountain. Then we load the next 32 houses, calculate their error, and take another step.
Ah, so we study the textbook in chapters.
Yes, we study in chunks. Batches are strictly for computational practicality, so one epoch might consist of many, many batches.
But wait, is there a trade-off there?
Always. If the batch size is too small, the calculated gradient is very noisy.
Why is it noisy?
Because maybe by random chance, those specific 32 houses you picked were all weirdly expensive mansions.
Oh, I see.
The model looks at them and thinks, oh, wow, all houses are incredibly expensive. And it takes a huge step in the wrong direction.
But over time, it averages out.
Exactly. It stumbles around a bit, but over the whole epoch, the average direction is correct. Now, if you use a huge batch size, the direction is perfectly accurate, but your computer runs out of RAM and crashes.
Engineering is truly always a trade-off. Accuracy versus speed versus memory.
Always. You can't have all three.
That clarifies epochs and batches perfectly. So I want to pivot a bit. We've talked extensively about parameters, the weights and the bias that the model actively learns.
Right.
But you just mentioned learning rate and batch size. Are those parameters too?
This is hands down the most common interview trap for junior engineers. No, they are not parameters. They are hyperparameters.
Parameters versus hyperparameters. Break it down. Who controls what?
Let's go back to our student analogy. The parameters, the weights, are the actual knowledge the student gains during the study session.
Okay.
The student learns that area is a very important feature. The teacher doesn't force that specific knowledge. The student figures it out by practicing and making mistakes.
The model learns the parameters.
Yes. Now, hyperparameters are the study strategy chosen before the studying even starts.
Oh, I see. So deciding I'm going to study for exactly 2 hours or I'm going to use flashcards instead of reading, that's the strategy.
Exactly. The learning rate, which is how fast we study, the batch size, how much material we study at once, the number of layers in a neural network, how complex the student's brain is allowed to be.
These are decisions we make.
Yes. These are decisions we, the engineers, make. We choose the hyperparameters. The model learns the parameters.
That is a critical distinction to wrap your head around. So if the model is the tutor, I am essentially the coach.
Exactly.
I set the training schedule, I define the rules, but the student has to actually get down on the floor and do the push-ups.
Perfect analogy. And just like a real coach, if you set the wrong strategy, if your hyperparameters are garbage, the student fails.
Which naturally leads us to the behavioral problems of our student.
Yes, the behavior problems.
Yeah.
We tease this in the intro with the student who memorizes versus the student who actually learns.
Let's put some formal names to these faces.
The two big ones in industry are underfitting and overfitting.
Let's tackle underfitting first.
Underfitting is when the model is just fundamentally too simple. In our exam analogy, this is the student who just didn't study properly, or they lack the baseline capacity to understand the material.
Like trying to solve a complex calculus problem using only basic addition.
Right. It's just not going to work. They miss the underlying patterns entirely. The predictions are terrible on the training data, and they're terrible on the test data. It just broadly fails.
Okay, that actually seems pretty easy to spot on a dashboard. The error is just stubbornly high everywhere.
Exactly. But overfitting, this is the incredibly dangerous one.
Overfitting is the memorization failure we talked about?
Yes. Overfitting is the most seductive trap in all of AI because it looks exactly like massive success.
Because your numbers are so good.
Right. You check your training accuracy, and it says 99.9%. You're high-fiving your team. You think you're a genius. You think you've completely solved the Mumbai housing market.
But in reality, you've actually just built a giant, useless lookup table.
You have. And here's a much deeper insight into why this happens. Overfitting isn't just about memorizing data. It is a fundamental failure of abstraction.
A failure of abstraction. What do you mean by that?
Think about a toddler learning to recognize dogs for the first time.
Okay.
If the only dog they ever interact with is their family's specific golden retriever named Buddy, they might construct a rule in their head that says, a dog is an animal that has golden fur, sits on the green rug, and wears a red collar.
Oh, I see. So if they go to the park and see a black poodle,
They confidently say, that's not a dog.
because it doesn't have a red collar.
Exactly. They have included the absolute random noise, the red collar, the green rug,
Yeah.
into their strict definition of the signal, the animal itself.
That is a brilliant way to explain high variance.
Yes. The model is so hypersensitive to the specific random quirks of the training data that it completely breaks when those quirks are missing in the real world.
That is absolutely terrifying for an engineer. You think your code is ready for launch, but you're actually about to drive the company car right off a cliff.
It is the #1 cause of failed AI projects.
Yeah.
And it connects deeply to another core concept we need to cover: bias versus variance. This is often called the archer's dilemma.
The archer's dilemma. Okay, paint the picture for me.
Visualize a target practice range. There's a target with a bullseye dead in the middle. You are the archer.
Okay, I have my bow in hand.
Bias refers to a very consistent error. Imagine your bow sight is physically bent to the left.
Right?
You aim perfectly every single time, your breathing is great, your hand is perfectly steady, but every single arrow lands in a tight cluster in the top left corner of the target.
So I'm consistently wrong.
Yes, high bias equals high error due to fundamentally wrong assumptions. This is underfitting.
Because the model is biased towards being too simple.
Right. It consistently misses the entire point. It basically says, I don't care about area or rooms. All houses cost exactly 50 lakhs.
It's stubbornly wrong. Okay, now what is variance in this analogy?
Variance is inconsistency. Imagine the archer has incredibly shaky hands. Or maybe they're trying to aim while jumping on a trampoline.
Sounds tough. So the shots are just scattered absolutely
That's
everywhere.
right. One arrow magically hits the bullseye, the next one hits the brick wall, the next one hits the floor. High variance means the model is aggressively reacting to noise. It is highly unstable.
Meaning if you change the training data even slightly, the model's predictions just swing wildly in random directions.
Exactly. So high variance is usually deeply linked to overfitting. An overfitted model is hypersensitive. It's aggressively chasing every single little outlier data point, so its shots, its real-world predictions, are totally scattered when it faces reality.
And the trade-off here?
It is the fundamental trade-off of all intelligence, artificial or human. To learn effectively, you actually have to simplify. You have to learn to ignore details.
Wait, that feels really counterintuitive. Usually we think more detail, more data is always better.
Not in mathematical modeling. If you don't aggressively ignore useless details, you cannot generalize to new situations.
I see.
If your housing model tries to mathematically account for every single random fluctuation in price, like the specific color of the living room curtains, or the mood of the seller on a Tuesday, it becomes completely useless.
Because those things don't actually predict the overall market.
Right. Generally, very complex models tend to have low bias. They can technically hit the bullseye, but high variance. They're incredibly shaky.
And simple models.
Simple models tend to have high bias. They miss the bullseye, but low variance. They securely hit the exact same wrong spot every single time.
So you really want to be right in the middle. Accurate, but steady.
That is the holy grail of machine learning. As engineers, our entire job is to tune the hyperparameters to find that exact sweet spot. We need the model to be smart enough to see the real pattern, but dumb enough to ignore the curtains.
This is great. I really feel like we've built the complete engine today. But before we wrap up, I want to do something highly practical. We promised at the start to make our listeners industry ready.
And that means understanding the industry jargon.
Exactly. Let's do it. I call this the translation drill. I'm going to play the role of the annoying senior expert who uses overly fancy words in a meeting.
Oh, I know the type.
You are the translator. You tell me what the expert is actually saying in plain, simple English. Ready?
Ready, hit me.
All right, phrase number 1. Let me adjust my glasses here. Looking at the logs, the loss is not converging.
Translation. The model isn't reaching a stable, low error. It is still confused and jumping around. It cannot settle on a final answer.
Perfect. Okay, next one in the daily stand-up. I think we need to reduce the learning rate.
Translation. We need to tell the model to take much smaller steps down the mountain. We're currently overshooting the valley entirely, so we need to be way more careful with our weight adjustments. We basically need to stop burning AWS GPU credits on exploding gradients.
Nice. Number 3. I've reviewed the metrics, and this model has incredibly high variance.
Translation. It is memorizing the noise in the data. It looks great in our controlled lab environment, but it absolutely will not generalize to the real world. It's shaky. It essentially thinks the red collar is what makes the dog a dog.
That's a great callback. Last one. To fix this, we should really increase regularization.
Translation. We need to mathematically punish complexity. We need to stop the model from memorizing by forcing it to keep its weights simple and generalized.
Punish complexity. That sounds harsh, but highly effective.
It is incredibly effective. And honestly, that actually leads us directly into our toolkit for the next step.
Right. We've talked extensively about all these massive problems, overfitting, high variance, non-convergence. We don't just stare at the dashboard and cry, right? We actually have ways to fix them.
We absolutely do. We have a very robust engineering toolbox. We actually just mentioned one, regularization.
Give me the quick preview. What exactly is it?
Regularization is a mathematical technique where we add a strict penalty directly to the loss function. We basically tell the model, hey, I want you to get the right answer, BUT. If you use massive, overly complex weights to do it, I am going to heavily penalize your score.
Oh, so it forces the student to keep their answers simple, like a teacher saying, don't write a confusing 10-page essay when a clear one-sentence answer will do.
Exactly that. It is the best way to mathematically prevent memorization. And the other big tool in our box is cross-validation.
What's that one?
So instead of trusting just one single exam score, we rigorously test the model on multiple different slices or splits of the data to see if its performance is actually stable.
Like giving the student 5 completely different mock exams to make absolutely sure they aren't just getting lucky.
Precisely. It proves they actually understand the material.
Yeah.
But we aren't going deep into the math of those today.
No, no. Today was all about building the engine. Next time's about opening the mechanics toolkit.
Exactly.
Perfect. So let's bring it all home for the listeners. Synthesize this for us. What is the one mental machine loop we need everyone to walk away with today?
It all comes down to 4 strict mechanical steps. Step 1, prediction. The model takes the inputs and makes a guess using its current, possibly random, weights.
Step 2.
Step 2, loss. We calculate the exact error using our disappointment meter, often squaring that error to heavily punish the really large mistakes.
Right, the mean squared error.
Step 3, adjust parameters. We use gradient descent, that mathematical sensitivity check, to feel the slope and find the exact direction downhill to reduce the error.
And finally,
Step 4, repeat. We just do this over and over, epoch after epoch, batch after batch, until the error is minimized and we hit the bottom of the valley.
that really is the heartbeat of machine learning. It's not magic, it's just iterative error minimization.
Precisely. It's just a machine turning knobs until the disappointment goes away.
Now, as we mentioned, understanding the engine is just step 1. But knowing how to practically tune it when it breaks is step 2.
And it always breaks at first.
Exactly. So in the next lesson, we are going to open up that toolbox we just teased. We are going to look at practical, industry-level engineering techniques to fix overfitting using regularization and cross-validation in extreme depth. You absolutely do not want to miss that.
That is where you really transition from being a student to a true AI engineer. That's where you learn to actively fix the broken model.
For now, I have a specific challenge for you, the listener. Go back through this deep dive. Try the translation drill on your own. Try to explain learning rate to your cat or your roommate.
If you can explain it simply to them, you truly know it.
And if you are stuck on the fundamental difference between loss and accuracy because they are very different things, write your questions down in the comments below. We actually read them and respond.
We do. We love seeing those questions.
Absolutely. Please like, share, and subscribe to the channel. It really helps us keep these free deep dives coming your way. Until next time, keep learning, keep adjusting your weights, and we'll see you in the next deep dive.
See you then, everyone.